Annenberg Media.
By the National Science Foundation, America's investment in the future. By the American Society for Microbiology. And by the Office of Biological and Environmental Research of the United States Department of Energy. Additional funding was provided by the Arthur Vining Davis Foundations. This program has been made possible in part by the Corporation for Public Broadcasting.
Attention all stations, this is the NTD performing the launch status checks. Verify ready to resume count and go for launch. Say go, no go. OTC. Go. Go. LPS. Go. 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 FTE. FTE go. LRD. LRD go. SRO. SRO go. You have a range.
What does a spacecraft, a canning factory, and a hospital have in common? At first glance, not much. But the truth is, millions of dollars are spent and thousands of people are aggressively working to make them very similar.
T-minus 10.
At least in one respect.
6.
Microbial control.
3, 2, 1. And liftoff.
Disinfectants, antiseptics, antibiotics, all are household words these days, and all are used to do basically the same thing: control microorganisms. But just who is controlling who here?
Sterilized and sealed for my protection. And they're on special. As we've already learned, microbes are everywhere, and they're not necessarily out to get us. They're just doing what they have to in order to survive and reproduce. However, there are times when exposure to certain microorganisms does present an element of risk. It's at these times that we attempt to control them. The level of risk and the adverse conditions that can result determines the level and type of control strategy used. I'm Jim Leinfelder. In this episode of Unseen Life on Earth, we'll examine some of the ways we attempt to control contamination and disease. Each of the environments we've just seen are, to a certain extent, just like this can of beans. They are all
controlled environments. NASA, for instance, aggressively controls and monitors the external and internal environments of the shuttles and other spacecrafts. This control is an attempt to prevent microbes from outer space returning to Earth, as well as preventing terrestrial organisms from hitching a ride into space. Microbial stowaways that could contaminate experiments. In other words, you don't want to send a craft to Mars only to discover life from New Jersey. In the hospital environment, various levels of control are implemented to prevent infection, from routine floor mopping to sterilization of surgical instruments. The food industry uses various methods to keep microorganisms out of foods, remove microorganisms from contaminated foods, and hinder the growth and activity of microorganisms already in foods.
But why do we want to control microorganisms? Well, there are several reasons, but basically we want to keep them from doing what they do naturally, growing on us, our food, and just about everything else we value.
Some contamination control methods, such as those used by the food industry, retard spoilage, thereby preventing economic loss and prolonging a product's shelf life. More importantly, though, contamination control is a health issue. whether it be in a store, in the hospital, on the street, or in our very own homes. It is an attempt to prevent encounters between us, microbes, or their toxins. However, in spite of our best efforts, encounters occur, and infection can result. Infection treatment is then used specifically to fight disease, and that can involve another form of microbial control, antibiotics.
In each case, a conscious aggressive attempt is being made by humans to control the level of risk presented by various microbes that we have deemed bad. How aggressive we are depends on the level of risk.
Home sweet home, a perfect place to demonstrate two methods of control, physical and chemical. Now, our homes don't need to be sterile, but this is certainly a place where a little control can prevent a lot of problems. This raw chicken could be a metropolis of living organisms. Back when it was being processed, the meat may have been contaminated by organisms that used to live in the gut of the bird. Those organisms hitched a ride on this chicken into my house. Now, those organisms weren't, and they certainly aren't now, a threat to this chicken. But if they get inside us, they can make us sick, so we cook it. Cooking kills most of the microbes we worry about. It physically controls them. Now, this head of lettuce, on the other hand, is usually fine after a brief rinse. That eliminates most of the microbes that might have hitched a ride from the field or while basking in the fluorescent glow at the market. Remember, you're not the only one who paws the lettuce heads before choosing. All right, salad. Oops. Oh yeah, I meant to do this to demonstrate a point. The chicken, once cooked, is under control, microbially speaking, and the lettuce, after a bath, was too. But I just contaminated their respective environments. By using the same knife and cutting board, I've mixed their microbes. If only I'd used a few basic physical and chemical control methods, I wouldn't be in this culinary conundrum. If I'd used a different knife and a different cutting board, the pathogens on the chicken would have stayed on the chicken, they wouldn't have contaminated the lettuce, and therefore me. And by thoroughly washing my hands after preparing the poultry, the soap acts as a chemical control, an antimicrobial agent, carrying unwanted pathogens down the drain. To prevent contamination, care should be taken to keep environments clean and separate. How clean is clean? Well, that depends on where you are and what you're doing there. Canning is one of the oldest, most reliable ways humans have controlled microbes. A combination of intense heat and pressure before and during the canning process creates an environment that microbes can't tolerate. It sterilizes the contents of the can. Sterilization is the destruction of all forms of microbial life. The sterile can is immediately filled with food, sealed, and heat processed. This prevents microbes such as Clostridium and Salmonella from contaminating the food inside, so the food remains safe and edible for a lot longer. It's a microbially controlled environment in a can. A sterile environment which stays sterile until the seal is broken and the food is exposed to another environment. If I eat this now, I may ingest a few dangerous microbes, no problem. But if I decide to take off for the weekend and leave this open can of soup to commune with nature, the microbes, who by the way never seem to rest, spend the weekend multiplying. And I eat contaminated bacteria soup rather than chicken soup. If I'm lucky, it'll just taste horrible. If I'm not, some of the organisms thriving inside could make me sick. A hospital is an environment where clean means many different things. It demands more awareness of and attention to microbial control than our kitchen, but can't hope to be as sterile as the inside of a can.
Jim, this is the emergency department. This is where patients...
Dr. Paul Lewis is an epidemiologist at Oregon Health Sciences University in Portland.
different thing about the hospital is that a lot of the people that spend time in the hospital are particularly susceptible to infections. Either they've had an injury that's broken their skin or their bones, they've had an operation that's opened up their body, or because of their own illness, they have a very weak immune system that has trouble fighting infections. In addition, in the hospital, patients get exposed to things that aren't always present in the rest of the environment. The microbial environment in the hospital is different because of the sick patients that are in the hospital that carry different microorganisms, and the fact that we use a lot of antibiotics in the hospital, and the microorganisms in the hospital tend to be a little bit harder to kill.
It's in places like this where microbes can gain the advantage in people and infection can occur. That's why it's so important to prevent contamination by using techniques such as disinfection, antiseptics, and sterilization. These methods of control attempt to destroy pathogens, thereby reducing the number of organisms to a level deemed safe by public health guidelines. Disinfection is the destruction of pathogenic organisms on inanimate objects, such as a sink or a hospital bed. Antisepsis refers to that destruction on a living object, such as skin. Disinfection and antisepsis are effective, but do not destroy entire populations. Endospores may survive. To destroy all forms of microbial life requires sterilization. One method of sterilization used in a hospital is the autoclave, moist heat under pressure. Not unlike the canning process, is used to sterilize everything from surgical instruments, some intravenous solutions, and even hospital clothing and blankets. A hospital also attempts to eliminate or control the sources, routes, or agents of infection transmission.
In the infection control program, we practice what we call 4 levels of isolation. And the first level of precautions is just called standard precautions, and this applies to all patients in the hospital. And for this, we just intend that all healthcare workers wash their hands before and after any patient contact. It's to prevent the healthcare worker from spreading any potentially infectious substance to the patient, and it also prevents the patient from spreading something to the healthcare worker, and from the healthcare worker indirectly spreading that to the next patient they encounter. The next level of isolation is what we call contact precautions. We take contact precautions in situations in which patients are infected with microorganisms which can be spread either to healthcare workers or to other patients, but they can't jump and they can't do it magically. They have to be spread by direct contact. But if a healthcare worker has direct contact with a patient, they need to be wearing gloves and to be wearing a gown to prevent contamination of their hands or clothing. The next level is what we call droplet precautions, and that's because they're spread in what are called large droplets, which actually fall out of the air within a fairly small sphere around the coughing or sneezing patient. In this situation, in addition to the healthcare workers wearing the gloves and gown to prevent contamination of their hands or clothing, they also wear a mask so that when they are providing care to the patient within that 3-foot radius, they won't inhale or have contact with their mouth or nose with those large droplets. And the final category of isolation is what we call airborne precautions. And this really is for those microorganisms that can fly. And that's actually a very small number. And that includes things like measles, chickenpox, and tuberculosis. And in these situations, we use our highest degree of isolation, in which the patients are actually kept in rooms which are actually at a lower pressure than the rest of the hospital, so that air only flows into these rooms. In addition, when a healthcare worker or visitor enters that room, they wear a special mask that actually has a high efficiency filter on it that prevents them from inhaling these organisms in the air.
Surgery is one area which demands a high level of cleanliness. Cleanliness which starts well beyond the actual operating room. Near the entryway, a line on the floor clearly indicates a point past which all must be wearing surgical attire, including cap and booties. Those who enter the operating rooms must do more to assure microbial control, starting with an aggressive hand washing.
Our surgical scrub brushes are impregnated with a variety of different disinfectants, which are known to be effective at killing the bacteria that inhabit the skin. Furthermore, the surgeons wash more than just the tips of their fingers. They wash all the surfaces of their hands and wrists, and actually up to their elbows. When a surgeon enters an operating room after having completed their surgical scrub, enter without touching the door, and before touching anything in the room, they are assisted in the donning of a sterile gown, and in general most surgeons wear at least 2 pairs of sterile gloves. The degree of cleanliness of the equipment in this environment has also reached the highest level, that all the equipment is not just clean, but it's actually sterile, and the sterility is documented.
In the emergency area, the various levels of control merge. Patients from outside the hospital enter an intensive care environment instantly. The atmosphere may seem chaotic, but the infection control protocol is the same here as any other intensive care area. Gloves, masks, and other barrier precautions are worn to protect patient and staff. The trauma rooms are stocked with prepackaged sterile instruments, IV solutions, and equipment.
There's no schedule here. When it rains, it pours. Sometimes nothing will happen for 6 hours, and then 6 patients will come at once. So it's sort of like the hurry-up version of infection control here, always being ready ahead of time and cleaning everything up as soon as each case is finished.
As soon as the room has been vacated, the cleaning process begins. First, the linen is removed to be laundered. Disinfectant is then applied to the bed, the railing, anywhere contamination may have occurred. Even the sink is disinfected. The various cleaning procedures used in a hospital are fairly successful at controlling most microorganisms. But as we've learned, microbes adapt.
A few years ago, we had a new drug-resistant organism enter our hospital environment. We wanted to make sure that our cleaning and sterilization techniques were adequate. So after a room in which a patient with this drug-resistant organism had spent a few weeks, we sent our infection control team in to actually culture the surfaces. And bed rails are one of the important surfaces that patients touch a lot and can contaminate with microorganisms. We just simply take these culture swabs and go along the entire bed rail, and we just keep going back and forth and really covering all the surface. After we've done that, we take this swab and we'd actually send it to the laboratory, but I'll just show you what we do. We'd actually go ahead and plate it on a selective media on which only this drug-resistant organism can grow. Then we'd take this plate with the selective media on it, send it off to the laboratory where it'd be incubated overnight. This is the plate I just used, but the result we'd be looking for would be like this. No growth of the drug-resistant organism on this selective media plate.
No news is good news.
Yeah, exactly. If it were not effective, we'd expect to see some bacterial growth. This is just an example, not from this bed rail, of what that growth would look like. Well, as you see here on this plate, there has been growth of the organisms. Each little dot there is called a colony. And bacteria grow very quickly. Each one of those last night were just a single bacteria. Wow. And overnight they grow at a very rapid rate. They double almost every 20 to 30 minutes.
And so how did things turn out?
Well, it turns out we did this for our first 10 patients that had this drug-resistant organism that spent a few weeks each in the hospital, that our disinfection techniques were effective because we failed to ever find those bacteria after the rooms had been cleaned.
Great.
Although these physical and chemical methods are very effective in controlling environmental contamination, many are far too harsh to be used on or in our bodies. One way to control microbes once they get inside us is through the use of antibiotics. We think of antibiotics as a recent invention, but microbes have been creating and using them for billions of years. Like all living things, microbes compete with one another for what they need. These tiny chemists routinely produce a wide variety of substances to vanquish their microscopic competitors. Among their chemical weapons are substances which we call antibiotics, substances that we have learned to manufacture and use in the treatment of disease. We've had great success controlling disease in two ways: prevention and treatment. Once we understood the principles of microbial control, our world drastically changed.
There were a lot more healthy, happy kids, for one thing. The probability that most of these kids will live long and happy lives is better today than at any other time in human history.
Today, people of all ages are susceptible to far fewer bacterial infections due to the use of vaccines and antibiotics. However, we must remain vigilant in our attempts to control microbes that pose a health hazard. For even though we have virtually eradicated diseases like polio, smallpox, and measles, there will always be microorganisms that can cause disease. Viruses, for instance, are still a major threat because there are very few effective antiviral agents. And although antibiotics have been successful in controlling bacterial infection, in recent years a threat has appeared on the horizon. Overuse of broad-spectrum antibiotics has created the specter of antibiotic-resistant bacteria. And although these measures have improved the overall health of many of the world's peoples, there are many more places where controls and their benefits simply do not exist. Contaminated water, lack of education, poor hygiene. They all contribute to make well-known and well-understood infectious diseases the world's biggest killers. Germaine Honquet is a physician with the international agency Doctors Without Borders. She has worked in Africa and is now working in Honduras.
In developing countries, a major problem is that the environmental, the water supply, the sanitation conditions, the level of hygiene, the level of education, the level of nutrition of the people, in general, the living conditions of the people are poor, and this is favoring the spread of those infectious diseases.
Worldwide, 50,000 people a day die of infectious diseases such as typhoid, tuberculosis, cholera, yellow fever, and malaria. These are not exotic diseases, and the strategies to control them have been known for years. The infectious diseases most problematic here are well understood. Germaine Honquet is a frontline warrior in the fight against infectious disease. The battle she wages every day could easily affect us thousands of miles away.
It's clear that infectious disease, they do not have borders, they do not respect borders. Nowadays that people are moving so much from one country to another country, every country is at risk almost at every disease.
And people are not the only things moving more often from country to country. The days of buying nothing but locally produced foods are gone. The tomato you buy today could have been picked on an entirely different continent just a few days ago. International food distribution means that much like the microorganisms that hitched a ride into my kitchen on the chicken, microbes can hitch a ride into our food supply from all over the world.
Ever since humans discovered microbes, we've struggled to control them, from controlled environments to prevent contamination and rot, to controlled environments to prevent infection. We've used techniques ranging from sterilization to antiseptics to antibiotics to tip the scale in our favor. But as we've seen, microbes, which have been evolving for 3.8 billion years, are pretty resourceful and have come up with ways to withstand some of the control methods we throw their way.
This has led to the almost frantic search for new methods of microbial control, which hopefully we will use more wisely. We not only share this planet with microbes, our lives are intertwined. For the most part, those relationships are in equilibrium, but there are a whole range of relationships between macroorganisms and microorganisms, from helpful to harmful. Those are the focus of the next few shows.
Annenberg Media.
By the National Science Foundation, America's investment in the future. By the American Society for Microbiology. And by the Office of Biological and Environmental Research of the United States Department of Energy. Additional funding was provided by the Arthur Vining Davis Foundations. This program has been made possible in part by the Corporation for Public Broadcasting.
For information about this and other Annenberg Media programs, call 1-800-LEARNER and visit us at www.learner.org.